Now a few more words about phasor diagrams. Phasor diagrams can be very useful, but again, like always, you have to have a lot of practice. And if you don't have the practice, they may scare you at first, and they may even confuse you. I will do one problem in which I will use phasor diagrams. That's my last problem that I will do, 7, because I will leave you alone with 8. I don't think 8 is all that difficult. L, R, C. And we have an alternating voltage source, E0 cosine omega t, and I think it's called E of S. And again, getting boring, I keep drawing the same circuit, C, L, R. I'm going to put a voltmeter over here. Nothing is new now. We've seen this now several times. I'm going to put a voltmeter VL over here. And I'm going to put a voltmeter over here. And now I also am going to put a voltmeter over here, which the authors call V out. Earlier we had 1 over L and C, you remember? And we argued that at resonance it always reads 0. But now I put 1 over L and R. Now, like in the previous problem whereby we had V4, which was over L and C, we now have to take the phase difference between this voltage and this voltage into account if we evaluate the V out. Well, this is now where a phasor diagram can be very useful. We treat the voltages in a way as vectors. If the current at one particular moment is I0, which is the maximum value, then the amplitude of the voltmeter over the resistance will be I0 times R. And I put that here as a vector. It is true that the voltmeter, the maximum amplitude of the voltmeter over the self-inductance will read I0 times omega L, but not at the same time that this one. It is ahead of this one. And it is true that the voltmeter over the capacitance, the amplitude, will be I0 times 1 over omega c, but it will not occur at the same time that this one does it. In fact, it will do it later. It is 90 degrees behind this voltage, and this one is 90 degrees behind that voltage. I can now make a vector diagram. This is a vector, this is a vector, and this is a vector. I add first these two vectors up. That gives me here a vector omega L minus 1 over omega c. And now I have here a vector, and this vector V, which is now the total voltage around the whole circuit, which equals the square root of omega L minus omega c squared plus R squared times I, which is I times Z. It's I0, because I have I0s everywhere. And here is that angle phi, the way I have defined it before. Now, all these four vectors, this one, this one, this one, and this one, rotate around in this direction with angular velocity omega. And the actual value that the voltmeter will read, that's the way you should interpret this phasor diagram, is the projection of that vector onto the horizontal axis. And so you can see when the voltmeter of the resistor reaches the maximum value, this projection is 0 and this projection is 0. I've stated that many times before. When this reads a maximum value, this reads 0 and this reads 0. But now if you have a quarter of a period later, this vector will be here, this vector will be here, and so this vector will reach, this voltmeter will reach a maximum. And this vector will be here, and this voltmeter reach a maximum. And this vector here, if you want to know what the voltage of the driver is, because this is the voltage of the driver, well, that's at E0 cosine omega t. And we call that E of S. When that goes around, it's the projection on the horizontal that at all moments in time gives you the driving EMF. And this is not so easy to digest, but once you get the hang of it, it's actually very nice. Because if now you want to know what the voltage is of the voltmeter that is attached to the self-inductance and the resistor, all you have to take into account is the phase difference between this vector and that vector. And so I will make a new diagram for that. This is the vector amplitude, IR times R, and this is the vector which is ahead, amplitude I0 times omega L. And so taking the phase into account, this will now be what the voltmeter V out will read, amplitude. This is over the R and the L simultaneously, which is I0 times the square root of omega L squared plus R squared. You see that immediately from this diagram, and this phase angle is not the phi that we have defined it before, but you can determine what it is. You can take the tangent, it's omega L divided by R, if you were interested in this. So we are looking at these voltages now as vectors. V out, 0 equals V amplitude R plus V amplitude over L. And the phase differences now have been taken into account. And so the magnitude of the output voltage equals I0 times this square root. And so if you want to know now what the ratio is of V out over ES, well, they have the I0 in common. So you would get then that you find here the square root of omega square L squared plus R divided by the square root of Z. I think you will have no difficulties finding this because this is ES, because E0, that's the amplitude of the driver, equals I0 divided by divided by Z. That's the definition of Z. And so, this shouldn't be too hard. And I think I'll leave you alone with this, because now that you have this, well, I think you are very, very well on your way.